Fmri is one of the most recently developed forms of neuroimaging. However, its idea to infer brain activity by measuring changes in blood flow and oxygen metabolism is not as new, with scientists exploring this technique as early as the late 19th century.
Conducting an fMRI brain scan requires a balanced table where the patient will lie down and slide into the magnetic resonance scanner, which is a large cylinder-shaped tube surrounded by a circular magnet. Because of the strong magnetic field that is present, the scan room should be free of any objects that would interfere with the signal. fMRI measures the blood oxygenation level dependent or bold signal. Red blood cells contain a high concentration of hemoglobin. The fMRI signal depends on the hemoglobin's molecule transportation of oxygen. If the hemoglobin molecule doesn't transport oxygen, it acts as a small magnet and interrupts the local magnetic field, resulting in a decreased signal received by the fMRI machine. Conversely, when the hemoglobin molecule does contain oxygen, it instantly turns transparent in the magnetic field. This change can be observed by the machine as a small but measurable increase in the resonance signal. As such, fMRI reveals what part of the brain is active during specific functions. When neurons in a specific region increase their activity, they consume the oxygen that is immediately available. Consequently, there is more deoxygenated than oxygenated blood in the area. This is demonstrated as a slight reduction in the bold signal, for a duration of 1 or 2 seconds. In the following 5 seconds, an abundance of oxygenated blood is transported to the area, which will demonstrate a gradual increase in bold signal. The final stage of the cycle is a steady return to baseline. This entire process is called the hemodynamic response function.
fMRI has many significant advantages, including how it is a non-invasive brain imaging technique, meaning it doesn't involve radiation, so that it is much safer for the patient. This non-invasive nature of fMRI is a big advantage over conducting X-rays, CT, PET scans, which all require radiation. Furthermore, fMRI is easy to use, making it a popular tool for brain imaging. With regards to resolution, fMRI has excellent spatial resolution, with the typical fMRI pixel size being about 3 mm, which is much greater than other techniques such as EEG. This allows us to visualize the activity of different brain regions with greater accuracy. While EEG and MEG each have great temporal resolutions being within the millisecond range, fMRI's temporal resolution is low, being limited by an intrinsic hemodynamic response, with bold response reaching maximum peak at about 5 seconds. A big disadvantage of fMRI that restricts its accessibility would be that it's highly expensive, with fMRIs being around $3 million. In contrast, the standard EEG typically costs $200 to $700. Plus, while with an EEG you can move a bit, the person being scanned with an fMRI must stay completely still in order to capture a clear image. However, fMRIs do at least provide clear images of body parts that can't be seen as well in imaging techniques like PET. And while fMRI acts as a proxy of neuron activation, EEG directly records neurons. Clinically, fMRIs are used in pre-surgical planning to localize brain functions, evaluate effects of stroke, and investigate brain disorders. Thank you.